In this video, I'd just like to go through some more examples using Taylor polynomials. To start with, suppose that the function f of x has the following 6-degree Taylor polynomial centered at x equals 0. The polynomial is what we'll refer to as t sub 6 of x equals 1 minus x squared plus 3x to the 4th minus 5x to the 6th. So first of all, let's find, given just this information, the kth derivative of f at 0 for k equals 0, 1, 2, etc., all the way through 6. So how do we do this? We have to remember the way that we define our Taylor polynomial, and in particular, let's think about the assumptions that we made when constructing the Taylor polynomial. So by definition, we constructed this Taylor polynomial so that t, not a subscript, the kth derivative of t evaluated at 0 would equal the kth derivative of f evaluated at 0. And in this particular question, we need to find the things on the right. So if I can find those same derivatives of the polynomial there evaluated at 0, that would allow me to find them for f. So to begin with, if I take my polynomial and I simply plug in the value 0, that would give me 1. But that has to then imply that f of 0 is equal to 1. So that's using our definition. I could then likewise take the first derivative of the polynomial. Doing so would yield minus 2x plus 12x cubed minus 30x to the 5th. If I were to plug in 0, I would get 0, and consequently, that tells me that f prime of 0 is likewise 0. The second derivative of my Taylor polynomial is minus 2 plus 36x squared minus 150 x raised to the 4th power. Plugging in x equals 0 to this yields minus 2. And that tells me that the second derivative of f at 0 is minus 2. The third derivative would give me 72x minus 4 times 150, so 600x cubed. If we were to plug in 0 to this, I would get 0, meaning that the third derivative of f at 0 would evaluate to 0. The fourth derivative of my Taylor polynomial is 72 minus 1800x squared. Plugging in 0 to that polynomial would give me 72. So that tells me that the fourth derivative of f evaluated at 0 is 72. And I just have 2 more to do here. The fifth derivative of this polynomial, we see now that constant term goes away. Now I'm left with negative 3600x. Evaluating that at x equals 0 would give me 0. So the fifth derivative of f at 0 is 0. And finally, if I find the sixth derivative, this would just give me the constant function negative 3600. So certainly evaluating that constant function at 0 gives me negative 3600. And that means that the sixth derivative of f at 0 must be negative 3600. So these are all things that we can answer knowing the relationship between f and its Taylor polynomial. However, there would be a quicker way that we could actually get to these answers. Right, the long part here was having to take effectively those 6 derivatives. So while that's a complete solution, there is an easier way. So the other thing we know from definition is we know that the 6th-degree Taylor polynomial of f of x centered at x equals 0 is the following. It's defined to be f of 0 plus f prime of 0 x. Let me leave myself a little more space for this. Okay, so I'm going to put it over here. So it's defined to be f of 0 plus f prime of 0 times x plus the second derivative divided by 2 factorial x squared plus the third derivative evaluated at 0 over 3 factorial x cubed plus the fourth derivative over 4 factorial times x to the fourth plus the fifth derivative evaluated at 0 over 5 factorial x to the fifth, and I didn't quite make it, the sixth derivative evaluated at 0 over 6 factorial x to the sixth. That's the definition. But somebody's telling us that for this particular function, that is equivalent to this. So what happens is I can take that polynomial that's given and match it to the general formula here. So if these two polynomials are the same, one thing I know is that their constant terms must be the same. So when I need to find f of 0, what I'm going to observe is that that is the constant function of the polynomial, and this is the constant part of the polynomial. And likewise, we can do that with all of the other terms. Notice that some of these pieces are missing in some sense. So if I want to find the first derivative, I see that that's the coefficient of x to the first power. However, when I look at this polynomial, I don't see an x to the first power. That is just a way of communicating that x to the first has a coefficient of 0. And that's how I would see then that f prime of 0 is 0. So if you were to go through and match like terms between this and the given polynomial, then that would be another way that you should end up at exactly the same bulleted list conclusions that we have here. It's important, though, to point out a cautionary example here. So as long as the polynomial is presented in the expected way. What do I mean by that? So this is given here that the Taylor polynomial that we're looking at is centered at 0, and we have factors of x minus 0 to the k in here. That means that we were able to use this more efficient approach because we could really just look at the coefficients and match those up. If instead I replaced this red box here and told you that what I was giving you was the Taylor polynomial, say, centered at 2, you can imagine that that would be feasible because while we're used to the definition having x minus 2 to the k, you could expand those factors and multiply out x minus 2 squared and x minus 2 cubed and reduce everything so that it presents in a polynomial like this. You would still be able to answer a question about find the derivatives of f at, say, 2 in that case, using the technique that we started with here, where I can match up derivatives. I would not be able to use the so-called more efficient method here, because in that case, I would be trying to match up a polynomial that has factors of x minus 2 to the k to one that doesn't look like that. So it wouldn't be as simple as just identifying coefficients. So that's why I wanted to go through the long way so that we know that that's always true for Taylor polynomials. You can find the derivatives of the original function by noting that they are equal to the derivatives of the polynomial only when evaluated at the center. And if it just so happens that the polynomial is expressed in the factors of x minus a to the k, you can actually just pluck out the coefficients in order to answer that. Okay, so same original given information. I have a function whose 6th-degree Taylor polynomial is centered at 0 is what's given there. But now I want to ask some different questions. So let's call this number 2. Decide whether you have enough information to find the following. And it's not asking us to actually find them, but just would we be able to do so? Again, just for reference, we're talking about an f of x whose 6th-degree Taylor polynomial centered at 0 is this. So I don't have to scroll back up. So a is equal to 0, and that's for f of x. So the first thing we want to consider is, could you find the 5th degree, Taylor polynomial centered at x equals 0. So thinking about our definition with our Taylor polynomial, that would require us to know all the way through the 5th derivative of f of x, specifically evaluated at 0. But of course, looking at what we did above, we know all the way through the 6th derivative. So the answer to this is yes, we would have enough information to find this. In particular, we can see that once I have a Taylor polynomial, you can find at the same center a Taylor polynomial of any lesser degree. So next one, the 7th degree. So the 7th degree Taylor polynomial, again, centered at x equals 0. And in this case, we don't have enough information. And just to be clear, if the question here, why do we not? We don't have enough information to find the 7th derivative of our function f at 0. Of course, the 7th derivative of my Taylor polynomial at 0 is 0, but that's just a reflection of the fact that we've only chosen it to go up to the 6th degree. That does not mean that the 7th derivative of f at 0 must be 0. And in fact, we simply don't know what it is. If we wanted to find the 6th degree Taylor polynomial for f of x centered instead at x equals 2. So we have the one centered at 0, and this question is asking us about the one centered at 2. And the answer is no, we don't have enough information for this. We only know the derivatives of f evaluated at 0, again, only up to k equals 6. And that doesn't tell me what they would be evaluated at 2. So we have these derivative functions of f, and we only know basically one point that they pass through, and that's at x equals 0. That doesn't tell me what they pass through at x equals 2. Part D is the 5th degree Taylor polynomial centered at x equals 0 for the function f prime of x. So I said it here, but I didn't write it down. These are all polynomials for f of x. So in this part, I'm saying a different function. So let's think about this here as a new function, calling it g of x. And you can think about, that means that in order to find the 5th degree polynomial for this function, we would need to know the derivatives of g up through the 5th derivative evaluated at 0. So we would need g, the derivatives of g at 0 for k equals 0, 1, all the way up to 5. But notice that these, because g is the first derivative of f, this is the same thing as needing to know the derivatives of f for k equals 1, 2, up through 6. And of course, we do know those. So this, I do have enough information to find. And then by the same token, what if we wanted to find the 5th degree Taylor polynomial centered at x equals 0 for the function f of x squared. Again, let's call this, so that's the prompt. Let's call this function h of x. And so in order to think about this, again, I need to know what is it that I have to find. So we need to find, again, derivatives of this function h for k equals 0, 1, all the way up through 5. And notice that in finding the derivatives of h, it involves f. So for instance, h prime of x would be 2 f of x times f prime of x. And of course, at 0, we would be able to find that from our knowledge of f and its derivatives at 0. So we would have enough information for that. And then we could use the product rule to find the next derivative, and so on. So because we have all of the requisite information for f up through the 6th derivative, then certainly we would have enough information for this. So again, we would be able to do this. It comes back to how we define our Taylor polynomials. And let's look at one more example. Different setup here. So we want to find the 2nd degree Taylor polynomial for f of x equals 4 plus 3x minus x squared near x equals 0. So keeping in mind our definition, I need to find 3 things. So I know that f of x is the given polynomial. We're looking at the Taylor polynomial centered at 0, so I want to find f of 0. I get 4. The first derivative of f is 3 minus 2x. Evaluating this at 0, I get 3. And the second derivative is minus 2. Evaluating this at 0, I get minus 2. So the Taylor polynomial in question here, by our definition, would be f of 0, 4, plus f prime of 0, 3 times x, plus the second derivative divided by 2 factorial times x squared. And notice that this simplifies to exactly the same thing we started with. So what we're seeing here should not be surprising, because if you think of the goal with Taylor polynomials, it was to kind of find the best polynomial approximation to our function f. If the function we start with is itself a polynomial, then it should be its own best polynomial approximation. So what we can generalize here is that if f of x is an nth degree polynomial, then finding the Taylor polynomial, to remember that this is my notation for kth degree Taylor polynomial. So this should be equal to f of x as long as k is at least as large as n. So in this particular example, I found the polynomial where k was equal to n. So a couple things to consider. Why is that polynomial, or excuse me, what's the reasoning for this relationship. In this case, notice that if I asked you for the third degree Taylor polynomial, any higher derivative higher than the second derivative for this quadratic function would be 0. So consequently, the coefficients of x cubed, x to the fourth, and so on would also be 0. So we'd get the same exact polynomial for any higher degree, and that would yet again equal the function. Why do we need it to be greater than or equal to? So if it were less than, notice like if I had to find the first degree Taylor polynomial here, that couldn't equal the function f of x because we could never get that x squared term. So it has to be at least as large as that. And the last thing I want to point out is that even if we had changed the center, if we'd looked for the polynomial centered at x equals 2, then we would still be able to go through and find the derivatives of f at 2 and write it out in the form of f of 2 plus f of 2 times x minus 2 plus f prime of 2 times x minus 2 squared. Now over 2 factorial. If you did that, you would be able to get the same exact Taylor polynomial and consequently the same function. And in order to connect those, you could actually multiply out the x minus 2 squared and so on to see that that's the case. So this fact is very broad. It doesn't matter what the center is, and this is just a statement about polynomials.